this computer. Okay, so now it's being recorded. So, okay, so after quite a long introduction, part of it because I like to speak too much and part of it because of technical problems, we are here in the initial part of this second section of our image processing course. And first of all, I wanted to show you what the following sections are going to be about, or following sessions are going to be about. So today we will speak about how to define images and the basics of openCV. In this second project, we will be processing images. So first, we need to know what images actually are. And today we are going to be speaking about that, perhaps a little bit faster than I intended to. Next week, we will speak about images as NumPy vectors. Those of you with previous experience have probably already encountered NumPy, but we will see how this parallel processing library can help us process images very quickly. If I have time, and that's in doubt now, I will show you a little bit of this at the end of this very session. We will see how to count pixels and how to manipulate images for labeling. And labeling is a big part of project number 2. We will do that also in the third session of this sub unit of the course, where we will try to combine that label manipulation, that image processing with NumPy with pandas, like the library that we already started seeing, to do some more large-scale manipulation. Not only manipulate one image, one mask, but perhaps many of them at the same time. And as usual, we will finish our second project with a Q&A session. So a session about questions that you have about the project and so on. So as you can see, we have basically 3 sessions of explanations and then 1 session of Q&A for project number 2. It's been published, have a look at it, and hopefully I get to explain to you a little bit about it in a few minutes, okay? Okay, so that's the overview. For the first goal, the first session, basically I want to tell you about what images are in computer vision. So we will see how images are basically matrices of pixels. And I don't know if you're very current on your matrices, but if you're not, we will see also a little bit about matrices. Basically lists of lists, collections, structure collections of pixels that we use for the representation of images. And we use images to represent our reality. So they are convenient, mathematical, primitive to store in the computer memory what we see, and also to change it, to manipulate it, to extract information from it and to build applications that do very complex things. And to do that, we will see how to define those images in Python. And especially, we will use the openCV library to manipulate images, to open and close them, and to store them in memory, and to read them from memory. And also the Matplolib library to represent them. So openCV will be more for using algorithms and for creating data objects from the images, and Matplolib will be to show the results and to be able to see the results on the screen. Okay. In particular, we will try to use some imaging functions from these openCV and Matplolib libraries. Okay, and here I have mentioned a couple of them. Okay, so specific goals, we want to open an image from a file with openCV, show it with Matplolib. These are the goals that relate to project number 2 specifically, okay? We want to understand basic image structure because we are going to be manipulating it in project number 2, and we want to present the project a little bit, okay? And I'm going to leave it here. Next week, we have another session, but let's do that one next week. To do all of those definitions, we can have a look at this session from courses number 4, and it's also number 5 about image basics, okay? These courses are part of this big data science specialization that started with basic programming. We also saw a little bit about data structures. You don't need to do that, but if anyone is very, very interested, you can see more about complexity. I don't recommend particularly for you. It's an interesting subject, but before that, I would say maybe you want to have a look at object-oriented programming. That's extra content for you, but maybe it can help you a little bit to use code libraries if you are not comfortable with that, okay? After all of this basic programming part is done, then we have a little bit of presentation about deep learning and artificial intelligence, and we in this course will do that next unit. And we have 2 application courses, so collections of notebooks for some particular goal. The one that is going to be more related to our course is this drone image processing course for forestry applications. We have been developing this with the people from the Faculty of Agriculture, and we will see some of the notebooks that we have developed with them here. Today, we see the image basics ones, and I have already listed some of the examples here, so you can have a look if you're interested. And you can just generally check this, but some of the units, especially 4 and 5, and all of these, the deep learning and computer vision basics notebooks here are more suited for the last unit of the course. Today, we will be seeing image basics and perhaps a little bit of WAS and document basics, because in parallel to this course about processing drone images, we also have this other course about processing scanned images from these WAS and documents, okay? Most of you come from forestry, so perhaps you're not all that interested, but I think it's nice to see how the very same techniques or some of the techniques are also useful for very different applications. I think that can give you a perspective of what is application specific and what's general. Programming and deep learning, in this case computer vision, are areas of knowledge that are always used in some other area of knowledge. This data science approach is always the same. You use techniques from more theoretical parts of mathematics, computer science in applied scenarios. Okay, so we will see a little bit about drones and hopefully a little bit about this completely unrelated thing about document processing, and we will see that some of the things that we do are exactly the same. Okay, so let's start with the basics of images. Please take some time to read this in detail. There is a video session that's less of a speed run that I am doing today, but so here you have a more detailed explanation. I'm going to stop just at some points. For example, the first thing that I wanted to stop about is this type of image. Okay, my artistic formation is pretty poor, but I like art a lot, so I just enjoy it as a non-knowledgeable person of it. But this is a type of painting style that makes heavy use of points, okay? And the people who paint in this way create a whole image based on making lots and lots and lots of small stains, small points with paint. I think these images are nice for me. They are compelling, but they also help me explain how information is stored in computer vision. In computer vision, we essentially do the same thing, okay? These people make many, many, many dots of different colors and use those to create a complete image. In computer vision, we do the exact same thing. We consider many, many, many points of information, points of color if the image is in color, or black and white if the image is black and white, grayscale if the image is grayscale. We call those pixels. And the main difference with this style of painting is that we set them in a very neat and regular way. We set them in a grid, in a regular 2D grid. Okay, so when we use this type of 2D images, what we really have is a grid of pixels. Okay, the way that we represent that grid that has two components, X and Y components, is by using a matrix. Okay, so that's the gist of it, but let's go a little bit to the beginning. Okay, for example, sorry, I need to import the images and so on. But anyway, here we can show a simple matrix. Okay, I have imported several libraries. If you're looking at the code, I'm using print-a-lot, and I'm using this display function from one of the libraries that I'm using. Okay, but basically I have this random matrix here. Okay, is the size of the font okay? Can you read this properly?
Yeah, it's fine.
Okay, thank you very much. So if I run it again, I'm going to have a different matrix, okay? And again, different matrix again. So I have a 3x3 matrix in this case. So 9 numbers, and I can index them in terms of their rows and columns. Okay, so these are the rows, and these are the columns. I have numbers ordered, sorted in this very neat and nice way that I was talking to you about. I have numbers set up in a grid. If instead of having just real numbers, I had colors here, or things that I could interpret as colors, I would have a very, very small image. Okay, so let's go and see exactly that, how a matrix, one of these two-dimensional lists, can be used to represent, to read, to store, to modify images. Okay. One small thing, I could have images in higher dimension. I could have images that are not 2D, but 3D. For example, in medical imaging, we have things like MRI or 3D ultrasound. Okay, so we in this course will be working basically with 2D images, which are the images that we are most used to, the ones that we take with our mobile phones. But 3D images are also a thing. So you're interested in that, we can talk about it. Much more difficult to process because of there are not so many around, there is not so much data, but also a very active field of research. For us, images will be 2D. Okay, and we will manipulate them with the openCV library, which we import with this CV2, and visualize them with Matplolib with that we see with this slightly longer import. We import it from pplot, which is a bigger library that has different parts. Sorry, from Matplolib, which is a big library, we import the plotting part and we give it a name as PLT. Okay, so then instead of having to write pplot or Matplolib point pplot all the time, then we just write PLT when we when we want to use it. Okay, so first of all, here we want to create an image that's a little bit bigger than the matrix that we made before. So we are going to make, an image that's 400 pixels times 400 pixels, and it's a color image. Okay, so we will define the size of our matrix as these 3 components: 400 times 400 times 3. That means that I will have a 400 times 400 grid, 400 times 400 matrix. So my matrix would be much, much bigger. Okay, I could just give this a 5. and I would have a bigger matrix. Sorry, no, because I only changed the showing part. I didn't change the making bigger part. Here it is, okay? Now I have made a bigger matrix, and I have a 5 times 5 matrix. Here I'm doing it 400 times 400, and I'm not doing it in the first example because it's going to be too big and I'm not going to be able to show much, okay? But here I want to define one of these 400 times 400 matrix, and I don't want to have only one number at each position, but I want to have 3. Why do I want to have 3 values at each position? Well, because usually color images are encoded in this system called RGB. So I have 3 visual channels, red, green, and blue, that I called RGB. And those allow me to visualize many of the colors that we humans can perceive. Okay? There are different ways to store images. We will see here binary masks, and basically we will work with grayscale images for those masks. Grayscale images do not have color, they have only one value, and you will see that that value is usually between 0 and 255. But here we want to encode to store color images. So we will have 3 values in every pixel to be able to make color, okay? And at first, I'm going to define, using NumPy vectors, a NumPy vector made of zeros exclusively, and call it my color image. Okay? So this makes a NumPy vector like a list of lists with 400 positions, and at each position it has 3 values. Okay? And I can access this like I used to do with my lists. I used an index to access my lists, and as we saw before, because this is a 2-dimensional list, a list of lists, I have to use 2 indexes. So if I print my color image of 0, 0, I get this 0, 0, 0 value, because all I have put everywhere in all of my 400 times 400 positions in each of the 3 values that each pixel has is 0. So I have something that's a very, very big and black image, okay? Not so interesting so far, but it is our first color image. It's black color, which reminds us a little bit of the famous joke from John Ford, I think, who at the beginning of the age of automobiles said that Americans could have cars in any color they wanted as long as they wanted black. So this is a little bit similar. We have a very nice color image, only happens to be completely black. As this is not very interesting, we can add a little bit more to it, okay? So we can, for example, define it in binary form. So if instead of having 3 values in each of my positions, I only have 1, this is automatically a binary or a grayscale image, okay? And instead of having these 3 values per pixel, I only have 1. See that as before, I have defined my color image here, access one of its elements. I have access 0, 0, but if I access 390, I will have exactly the same thing because I am only putting zeros into it. And now I'm defining another image that I'm calling my binary image that has the same 400 times 400, but then it has only one channel, one value per pixel, okay? So here I have different matrices, all of them look very black. And as I was saying, let's just add a little bit to it, okay? Let's define the color image again, same thing again, the binary image again, and let's use one function from openCV to add an ellipse to my color image, okay? Let's not look too much at the parameters, but basically I'm considering some principal axis and some ellipse center that are in relation to the size of the image. So you can look at this, but it's not very important now. But basically, I'm drawing this red ellipse here. Okay, the red color comes from here. As I told you before, all of the values of the pixels are in this RGB encoding system. So it has 255 maximum red, and it has no green and no blue. Okay, so this is basically a red ellipse that I can see here. Okay, and then I can also draw a rectangle, for example, and I have centered it in this with these two corners, 220 to 20 and 375, 375. So this is 220 to 20, this is 375, 375, and I have painted it in my binary image in 255 in white. Okay. As we are seeing, black is always encoded by 0, be it in binary image, it's 0, 0, 0. Sorry, color image is 0, 0, 0, or binary images as one single 0. Okay. So I have defined very simple images, binary format, color format, and I have added some objects to them. I have painted some things into them using these functions from the openCV library. But the main point here is that my images are matrices of pixels. Okay. I hope that helped a little bit. But mostly we will not be doing this. We will not be creating images from scratch. We will do it from time to time, especially for mask manipulation, but that will not be what we do all the time. What we do all the time will be reading images from file and changing those, or creating new ones starting from those that we have read from file. And to do that, I'm going to remember when I run the first cell, this one is using widget to download things, okay? So I actually downloaded a couple of images that I can click here, and I can see, for example, the first one. And now using the image visualizer inside of Google Colab to show this image called circles, which is made up of, who would have guessed, white circles on a black background. Okay, so there we have it. But now I would like to be able to open that one and to manipulate it using Python, and using, in particular, openCV. To do that, I'm going to be using the Imagre function. Okay, Imagre, creatively named after image read. This one is one function that you are going to be using in project 2, and that's basically what you have to do in task number 1, if I'm not mistaken. Basically, I defined the path to the function as I have downloaded them to what would be the root of my Google Colab machine. Remember, this is not running on my laptop. This is running on this distributed Google Colab machine. Then I have downloaded these images to the root of that machine. So my path is just the name of the image. I find the path, and Imagre receives the path, the place in my computer in the computer where this is running, where the image is, and then I have also given it a flag. In this case, Imagre grayscale. So I'm telling Python to read this image as a grayscale image. So an image that only has one value for every pixel. I could read it as color too, but I don't want to. Actually, let's see if I just, so let's first run this, okay? I have read the image, I have printed one pixel, another pixel, so this 0, 0 pixel is a 0, this 3020 pixel is around here, and it's a 255 because it's a white pixel. And what would happen if I read this as a color image? Then I still have the same image, if you realize, but the pixels have 3 components. Okay, so the black pixels is still black, but it's now called 0, 0, 0, and the white pixel is still white, but it's now called 255, 255, 255. If all values of red, green, and blue are maximized, I have a white pixel. Okay, that is not what I want to do, but this shows you that with the same data, Python can represent the information in different ways. Okay, in this case, grayscale or color images. Let's go back to grayscale, which is going to be a little bit simpler. So I have all of this red image, and I can access it as a list of pixels. So that's the basic structure of images in Python. Okay. Let's just manipulate it a little bit more. For example, here I can make a sub image. We saw with lists that we could select parts of the list. For example, in project number 1, you read every line, put that one into a list with the split for strings, but that had a date and a column number, sorry, the row number that you didn't want. So many of you did things like select with something like list slicing, my list of something to and semicolon, for example. Sorry. Okay, not power off the computer. What are you doing? So try again. Yes, thank you. So with 2 and a semicolon. So that means that we would have taken from position number 2, the third position, to the end of the list. Okay. That was how I selected sublists before. In this case, I have more than one component. So if I want to select a sub-image, only a part of the image, I can do the same thing, select from one position to another into different components. So in this case, I'm choosing the part of the image that goes from positions 18 to 30 and from 18 to 30, both in X and Y. So 18 in X, which happens to be the vertical axis in openCV, okay? It's this one, so 18 would be here, to 30 would be somewhere around here, because 50 is there, and the same thing for the horizontal y-axis, okay? From 18 to 30, so you would have something like that, okay? So let me run this. I have selected a sub-image and I have copied it because I don't want to have the same information pointed at by different variables. I want to completely copy all the values of these pixels in a different variable. So in case I change it, I don't change the original one. That can happen. Okay, we will go back to that. That's called aliasing. But I have made this copy. Okay, I have also painted a rectangle in these starting and ending points, which I defined at 18 and 30. Okay, 18, 18 and 30, 30. Okay, so I have painted a rectangle here and I have given it a 125 color. If 0 is completely black, 255 is completely white, 125 is a gray color. Okay, so basically I have painted this gray square here, and I have also created a new sub-image with a copy of what's inside of this square, okay? There is also a thickness parameter, which you might want to look at, but my point is that here, if I print the matrix corresponding to this sub-image, okay? Again, I have copied this here, I wouldn't have needed. I can display that image, and what I have is the values of 125 that correspond to the border of the square that I have just drawn. The black part in here, small but bigger here, are all of these zeros, and the white part from the circle is represented as this all of these white pixels. Okay. So again, in this case, grayscale images, but with color images, it would be the same. We just have different values here with 3 values in each of them, different pixels here with 3 values in each of them, are matrices of pixels. Okay. And we will manipulate them with this type of things, with this type of list slicing. We can traverse them if we want pixel by pixel, or although we will not recommend that. We will do that once, but I do not recommend it because it's very slow. Okay. And we have seen in general the structure of openCV images, how we store images in Python and in computer vision. Okay. Couple of things. I have quickly said that contrary to common sense, this horizontal component is the second one, and this horizontal, and it's called X usually, sorry, it's called Y usually, and this vertical component is the first one and is usually called X. So instead of being X and Y, openCV usually stores it the other way around. openCV is annoying and quirky in that sense. Okay, very useful, but has some annoying things. Another annoying thing that it has is that if we try to read another image, this tanuki means this animal, raccoon in Japanese, castor in Espanol, but tanuki, Japanese, raccoon in English. Sorry, I don't know about the Italian. We can see this image here, but if I just read it with openCV and I just plot it, I get kind of a weird color. I get this image. Okay. So I read the image as it is, and if I just plot it, I get this strange change color. Okay. Let me do it here, because it's going to be, this is the pretty one with showing with openCV itself. Okay, let me explain this properly. Here you have 2 slightly different color versions of the same image. Okay, and what I have done here is that I have read it here as an image, and I have created a second image too, doing something slightly weird that I will tell you about in a second. Okay, and then I have plotted them. First, the image as I had read it, and second, this modified image. The image as I had read it is slightly off. The color is not the proper one. Okay, this is the proper color. This green is slightly different. The whole colors on the raccoon have changed. Okay, here you have the comparison. This is the proper way to see that image. What has happened? Well, another quirk of openCV has happened. openCV doesn't store the colors in RGB order as the rest of the world does, but because of some strange reason, when openCV was built initially, the order of the colors in openCV is BGR. So not red, green, and blue, but blue, green, and red. Green is in the same place, but blue and red are swapped. Okay. So if we want to open things with openCV and then visualize them with Matplolib, with another library that expects things to be BGR, we have to do this change. Okay, this change is an example of very Pythonic is the word, very Python oriented way of writing things that essentially is traversing all of the list, and for every pixel, it's running over its 3 components and it's inverting them. Okay, it's going from start to finish, down up. So this is reading first the last component, then the second, and then the third. And this is effectively changing the BGR representation from openCV to RGB again. Okay, so this is technical. This is to show you that sometimes things have, let's say, a deeper, annoying component to it. But the main thing here is that even though it's not a super big problem, if your images that you're showing for project 2 have somehow a weird color, or all of a sudden you're probably running into this. Okay, I will give you functions that mostly take care of that. You could also just do like I did here and just use openCV for visualization, but that is usually a recipe for failure because this is not very good with big images, and our images are going to be pretty big. Okay. Okay. So main thing here, images are matrices of pixels, and those pixels can be one-dimensional here if we have grayscale or binary images. Binary are just grayscale images that only have black and white and have no grays. So this one is clearly grayscale because it has both black and gray and white, and also gray. And we have also seen some basic functions from the openCV library, some basic methods to read an image in color or read an image that's grayscale, for example, here. And we have done some simple accessing of some of the pixels. We have defined sub-images by selecting some of the, some of the pixels in the two existing components. And we have done small modifications using functions, in this case, drawing rectangles or ellipses here. Okay. So that's mostly it for image basics here. I wanted to show you just very quickly, it have taken a little bit more time, but for the problems, these basics for wasn't documents, where in a different type of course, I try to also present. Here there is quite a lot about reading PDF formats, because in this document processing community, of course, PDF is a pretty big thing. But here you can have a look, and I'm doing essentially the same thing, a little bit more complicated, but I'm again using paths to imread functions, okay? And I'm bringing them in color. Here I'm using a different function called CBT color, where I'm doing the same thing I just did, but in a bit more of a function-oriented way. I'm changing BGR to RGB, so I don't have problems visualizing things, okay? And then I am showing images, the same image in color and in grayscale, okay? You can have a look at those. Those are really cool. Then I'm using the same thing that I just did. I'm using sub-images to select parts of those lists of lists and show only small sections of the previous images. In particular, here, I am taking this part here and showing some things that are of interest for the exercise that we are doing there. Okay, so if you're interested in, if you want to see some cool Japanese documents or are interested in getting a little bit more practice for these image basics cards, here you have some examples, okay? And if you can follow that, then I do some very simple calculations, for example, adding up the percentage of black pixels there. Okay, this is mostly for more advanced students, but beginners, you can also have a look at this. Here I'm adding all of the pixels in the image that fulfill this property that are equal to 0. So I'm adding up all the pixels in the image that are black and then doing some computations for them. This is helpfully enclosed in a function called percentage of black pixels. So here you have some more examples of function too. Okay. I do the same thing with the percentage of white pixels. And the pixels that are white are those that have 255 value. Okay. And if you're a little bit disoriented by exactly what this is, this one full image is equal to one value, what does that even mean? Then you're on the right frame of mind, and I will tell you all about it next week when we talk about how NumPy helps me process images very quickly in parallel. Okay. So that was quite the speed run. I'm going to dedicate the next 5 to 10 minutes to project number 2 and to pointing out where all of those things are. This was a little bit quicker than I would have liked, but I think it was more or less fine. Please take the time to read through it. You can watch the video about the session that the notebook that we just saw and ask me. Okay, this is not difficult, but this is completely central to everything that we have to do in project number 2. Okay, so before next week, make sure that you're properly understanding this. Okay, now I need to go and find project number 2, which was conveniently opened in the other computer. So bear with me for a second. Those of you just was watching the session recorded, there were lots of problems with technical things at the beginning, and that's why I need to jump to this. As I told you before, we have 2 versions. We have an English version and a Japanese language version. The Japanese language version was done with the help of course, AI translating tools, my own meager Japanese formal language skills, and the invaluable help of Moritake Kouma, the TA for these and other subjects, who gave it a good read. So the Japanese is supposed to be okay, but it has not been tested. Okay, so if there are problems, if there are things that are not completely correct, or there are things that you don't understand, especially, let me know. As I said before, please begin today. If you let me know on the day of the submission, I'm probably not going to be able to help. Okay. So let me open yes, I have the English version there. Let me also say that the deadline for this is, as you can see here, June 14th. Okay, so let me just get a calendar out. That means that we have this session today, one more session next week, another, and then we have the submission on the Sunday of that week. Okay, this is going to be the Q&A session, and this is going to be the submission. Okay, so in all, we're going to have 1, 2, 3, 4 sessions for the second part, and that's done on purpose to leave a little bit more time for the third project where we do a little bit more complicated things. In terms of coding, many students in previous years have found project 2 easier than project number 1. I would say that the coding is actually more difficult, and the things that are done are actually more difficult, but perhaps the getting used to it and starting thinking about programming happens more in project number 1, and people are a little bit more up to speed in project number 2 and find it easier. But again, I recommend that you start as early as possible, and ask any doubts that you have. Remember that you can submit everything as many times as you want, and I will give you feedback. Feedback might take a little bit of time, okay? So give yourselves and me some time to think it over and to react, okay? Project number 2, I'm going to be explaining it in much more detail next week, but we are going to be working with images from the forestry department. They are downloading here. Let me see if I have, no, I don't. I will explain them later, but basically we have images taken with a drone from the Ensuring forest near Tsuruoka. Yamagata University Research Forest. And we are going to be doing some manipulation with them. We have lots of sites collected in this data Sara. You will learn about who Sara is. And actually, Sara happens to be back in Japan these days, and you might have, those in Tsuruoka might have met her these days. But basically, we are going to be manipulating this type of mosaics, and hopefully I can open it in the Colab viewer. Yes, this type of forest mosaics in Python. And we are going to be reading them as color images in openCV, and we are going to be using also lots of binary masks that encode information about where the different species of trees happen to be in those really big mosaics. Okay, so have a look at project number 2 and about what it speaks about. We will see more about it next week. But basically, you have a whole code. It's up here, difficulty 1, 2, and 3. So this is a little bit more structured than it was in project number 1. Difficulty 1, everyone should be able to do them. Difficulty 2 should be doable, even though maybe a little challenging for beginners, and easy for already people who know a lot about programming already. And difficulty 3 should be something that's a little bit challenging even for those that have previous knowledge. Okay. And the first task that you have to solve is basic image manipulation and things like loading an image using openCV. And we have seen all about that just in the notebook that we have been seeing. And if you take a close look at this image, you will see that this calls the proper function and also includes some functions to change this BGR into RGB. So you can use these functions that exist in some of the notebooks if you want to. If you don't want to use them, you can also do something different and just left them in case they are useful. Okay. Then you have a function to load binary masks, and you can again use the functions that you have up there or do something different if you prefer. Most of the interesting things here happen from this simple mask manipulation in the second task. Okay, so we are going to be seeing, as I was saying, that these binary masks show the positions of trees in all of those mosaics that we saw before. Again, more on this in detail next week, but we will want to use this information about the position of trees to compute different things. For example, when the annotations are not properly aligned, how many trees of each type there are, the areas of the different types of trees. You can find all about it down here, okay? So if you want to begin, you can have a look at this initial part, read the images, see how the images look like, and then when you get to task 2, you can start thinking about simple mask manipulation. If you want to solve this completely and properly, you will want to go back to the index of the course and have a look at the session, at the notebook that we will do next week, the one about NumPy for drone image manipulation. Today, we have been seeing the basics of image programming, and that's enough. Image processing. Images are matrices of pixels. Sometimes they have one channel and they are grayscale or binary, and sometimes they have 3 channels and they are color. They could have more channels, more on this next week too. But then after we have done that, we are going to be working with this manipulation of masks and juggling at the same time the color images and the masked images. And if you want to do that, I recommend this second unit of the course, NumPy for drone image processing. Okay. Okay, I think I'm going to leave it there. I'm going to leave you with also the advice to, if you want, have a look at Unit 2 and at the example, because those are other examples of how to look at different manipulations of data, different images, calling functions from library. I'm probably not going to be doing them in the course, but they are, I think, interesting reading. And you can also have a look at Unit 1 from the Wasan course if you want to have a look at that, and even a little bit about Unit 2. Okay. Is there any question about all of these things that I have been talking about? Okay, no particular questions, no problem. I'm going to stop now the recording. We will consider the session concluded. Okay.